Okay, let us start. Our Anna is not coming, she is sick. Okay, the first thing which I wanted to talk is how can we recover the back measure. How the back measure is obtained from the lower measure. Let us consider the following set. Let us fix n is an infinite number, and we consider the following set T 0, 1n, 2n, and minus 1 divided by n. So, now, what is this? If n is like this, we consider the following object. Tn equals 0, 1 over n, and so on, n minus 1 divided by n. If n is just a plain integer. So we have this sequence Tn. This sequence can be continued to the internal sequence. N is n. Internal sequence. Tn star n, n less or equal than some n. Yeah. So we can always take a sequence. This is a sequence of finite set. We can continue it to the sequence, to the infinite sequence, from 1 to from 0 to this, and this is an internal object. Okay, now for this T, it is our space, our basic set, and consider internal subsets of T. Internal subset. Then we can define the counting measure. It is this ratio, the number of element of A and number element of T. Yeah, this number of element, no, what is number of element of A? It is some non-standard integer. Yeah, so we can define it for internal sets, and we cannot define it for arbitrary subset. As set in the set theoretical sense, A can be even uncountable, and usually it is uncountable, but as internal set, it can be defined its number of elements, which is non-standard integer. And the same for the number element of T, which is just n, which we chose. Yeah. So this way we have the setup to define the Lloyd measure. So for any internal set we have this measure, but this measure is not sigma additive because the algebra of these sets, of the internal sets, is not sigma additive. So we have to extend it. So as I did before, we define A, the algebra of internal subsets of T. And now we can extend it. We can define corresponding sigma algebra. Sigma algebra is extension of this algebra, sigma of A. It is sigma extension of A. Yeah. So it is the smallest sigma algebra which contains A. Sigma extension of A. And as I explained last time, we can extend our measure, counting measure of internal sets can be extended to this sigma of A. So let's call sigma, let me define it, denoted mu of A. Sigma extension of mu on sigma of A exists. Why it exists? Because we have a general Theodori theorem which says that it exists if only this measure is sigma additive on the elements of algebra A, which themselves are the unions of countable set of elements of A. Yeah? So it is the minimal condition so that sigma additivity holds at least within this initial algebra A. Yes, so it is at least self-consistent within this algebra. And here we have a happy situation that it holds because no element of algebra sigma algebra A is no element of algebra A is the sigma union of other elements of algebra A. It can be maximum union of finite number of such elements. Yeah, therefore the sigma additivity on A holds automatically. So there is the situation when we have to check it, it simply does not appear. Yes, and now we have to add the sets which have measure 0, null sets. So null sets are sets such that they can be contained in some elements of the sigma extension of arbitrarily small measure. And we write sigma L it is sigma, let me write. We define okay, exists. It is mu sigma. Yes, and we write mu sigma of A equals standard part of the counting measure of A. And if we have null set, for this null set we set mu equals 0, and we write define mu L of A union B equals standard part of mu sigma of A if A in this sigma extension and B is null set. And this way we define a complete algebra, a complete measure. So we have an algebra such that together with each set it contains the set plus any null set, and the algebra, the sigma additive measure such that for null set it is 0. And this, so we have triple. We have this algebra L, our set T, our space. We have algebra L of A. It is this algebra of sigma extension of algebra A plus all null sets. And mu L. Mu L is this measure. And this triple is a measure space, and this measure space is regarded as a standard object. So this measure is this sigma additive measure with values in real numbers, positive real numbers. In this case, even numbers between 0 and 1. Okay, now how can we get a Lebesgue measure? How we did it? So let us define Lebesgue measure. So let us define the following sets. M is the set of standard set, subsets of 0, 1, such that the of V what is standard minus 1? Of B is the set of T in T such that standard of T is in B. So we consider these sets. And for these sets, we define measure. Define lambda of V is Lloyd measure of standard minus 1 of B. B is such that this measure does exist. So the theorem is that 0, 1 M lambda is the Lebesgue measure space. No, this means that M M is the completion, Lebesgue completion of Borel algebra and lambda is the Lebesgue measure. So what does it mean? Borel algebra, it is algebra which is obtained from segments or intervals in 0, 1 by the countable unions and intersections and complements. So if you apply countable number of times these operations, or finite or countable number of times in some order, then everything which you get is Borel sets. If you add on Borel sets, we always can define the Lebesgue measure, because Lebesgue measure is countably additive. And we also add the null sets, Lebesgue null sets, such that the measure is 0. So this means that they can be included in Lebesgue measurable sets of arbitrarily small Lebesgue measure. Yeah? And so we have this Lebesgue completion. Now, what should we prove? The construction of Lebesgue measure is itself a subject of the course of measure theory. So I'm not going to repeat all this. But what we should prove, in fact, essentially the only thing we should be proved is the following. So if you have the segment AB in 0, 1, yes, then this segment AB in for all AB in 0, 1. So this is what we have. We should be proved. But this is easy. Standard minus 1 of AB, standard T. I mean elements of T such that their standard part lies in AB. This is not internal set, so we cannot apply our science to this. Yeah? So we have to somehow reduce it to internal sets. We can write the following way. It is intersection of the following sets. A minus 1 over n, b plus 1 over n. We take this. Okay, should intersect it with T, because part of this, if B is, say, 1, or A is, say, 0, part of this goes beyond our segment 0, 1, so we have to intersect with T. This external set is the intersection of these internal sets. Yes, for internal sets we have already our measure countable, additive, and so on. Yeah, so therefore we can define the measure lambda of AB equals mu L of this set A minus 1 over n, B plus 1 over n, this set is a countable intersection of measurable sets. All internal sets are measurable, log measurable. Yeah? So this is log measurable set, and it's if you find estimate the counting measure of these sets, it is simply b minus a plus 2 over n. Yes? If you take intersection, and mu L itself contains the standard part. Yeah? So why are you so sad? Something's wrong. Okay, I hope it will be better. Yes, it already contains standard part, so we don't need to write once again standard part, and we have that this measure is the limit, the mu A of this is limit when n goes to infinity. It is simply b minus a. So lambda of ab is simply b minus a. No, that's it. So we have to start from something basic. Our basic sets are segments, and now we can consider their countable unions, intersections, and so on. And we get the Borel algebra, and then add the null sets, and that's it. So this way we can define the measure on the segment, which is exactly the Lebesgue measure. So it is great that Lebesgue measure is so universal, so fundamental that it can be obtained from completely different side. No, okay, it was, it is not, I would say, not so interesting now, because I want to go to probability, namely to construction some random processes. Yeah, so I would make a statement, yeah, that nobody knows what is probability about. What is a random event and what is probability of this event. It is believed that Kolmogorov and some other great people did lay foundations of probability theory, but they laid foundations for mathematics of probability theory, not for probability theory itself. So this notion that probability is a measure and so on is already mathematics. And so what is probability itself is quite unclear. And what I will tell you is no, in some part relies on our understanding of probability. No, consider the simplest random event. It is coin tossing. Yes, so we take a coin, toss it, and see what will follow, heads or tails. What does it mean that it is random and the probability of each outcome is 1/2? Yeah. Here, one understanding is that if you take a coin and toss it many times, say n times, and then we take the number of tails and number of heads and divide it by the total number of tosses, then the result will be, in both cases, close to 1/2. Yeah? But sometimes, and in fact it is most of the times, we principally cannot do it. Say, if the result of tossing the coin somehow affects who is tossing, say, for example, if it is coin heads, you will hang it, and if it is tails, you will be, say, burned on stake. This means that you have just one toss. So here, principally, there is no series of many tosses. So this statistical definition of probability makes no sense. So we have to think about different meanings. No, other meaning is principally different. Say we have n experts, yes, and these experts, each of them says his opinion. What is the outcome of this tossing? Yes, and we take the number of experts who say that it will be heads, and the number who say that it is tails, and divide both by the number of experts, and also have approximately half and half. Yes, so here at least it makes sense for just a single trial, but we have to somehow postulate these experts. Yeah, so experts should come from somewhere. Yeah, so this is also unclear. So something should be postulated. We can, for example, look closely into mechanics of coin tossing. Maybe from these mechanics will be clear what happens, why we think that it is probable that we have heads and tails. Yes, about 10 years ago, I remember here was a talk in Theorem exactly about this problem, mechanics of coin tossing. And the result is that it is almost never fair. I would say that the result, so if you coin, say, heads up, and then toss it arbitrarily, then with probability strictly more than 1/2, you will have the result heads. Yes? Sometimes it depends on how you toss the coin. You can be I would say, skilled in this, that this probability will be close to 100% that you will have the same sign as you started from. Yes, why? It is interesting. So the coin is a disk. Yeah. Now consider a normal vector to this disk in its center. Consider the motion of disk when the coin is already tossed and when it is in flight. Yeah. So this normal vector will describe, mechanics says that this normal vector will describe some cone, some circular cone, something like this. Yeah. So the coin will rotate this way and it will flip this way, but all in all, this vector, it should be perpendicular, describes a cone. Yeah. Now, if you try to do it accurately, then you have a approximately a cone something like this. So this means that more or less half of the time it is heads up, half of the time it is tails up. Yes? So in this case, you have nearly 1/2 probability that it will fall either side. If it looks like this, yes, that it always falls up the same side. Yeah. And we have only one case when this tossing is fair. This is when this cone is just circle, yeah, in vertical plane. In this case, it is fair. Yeah. So this means that this paragon of random event with probability 1/2 in fact has different probability and is practically never fair. So what does it mean? This means that we have to somehow postulate that there exists something like this coin, which is fair. Yes, and stop asking what does it mean. So it is a new entity, a new sort of entity, which is not reduced to anything previously existent. So it is a new thing which is postulated. Yes, and so it is a random variable such that the random variable which I z random variable z it can take say 1 and -1, just two values with probability 1. Probability of 1/2 each. So and we have to stop thinking what is the nature of this z. Now what I'm going to do today is to construct the Wiener measure or the Brownian motion, or better to say the white noise. So what is this? We have the segment 0, 1, and for any segment AB, we consider, so we should have a random value psi depending on A and B. Random value. Such that it should satisfy the following properties. That psi A, B and psi C, D are independent if AB and CD, if it can be even said this way. And CD do not overlap. Second, psi AB has and psi A plus H, B plus H have the same distribution. So they are equally distributed. And how they are distributed? Let me if you have say U, V in R, segment U, V in R, then you have that probability of the event that C, A, B in UV equals 1 to pi B minus A to the power 1/2 integral from U to V E minus y squared divided by 2 B minus A dy. So this is a Gaussian random value, yes, and its dispersion sigma square equals B minus A. So we have a system of such random quantities. System of such random quantities. We can add other requirement, which is that if you have, it is 4, if you have A less than B less than C, then you consider C A C equals C A B plus C B C. So what does it mean? So anytime we take the realization of this process, so for any segment we have a corresponding value, then we have this. So it depends on random argument omega, So we have this. And now, having this, we can define the linear measure, or linear random process. Linear random process, or to say random function. Yes? So what is linear random process? Is W of T omega equals C 0 T of omega. So we fix the first and we change the second, and for any omega in our probability space, we define this function. So it is a random function. Okay, so how can we build it? Up to now it is just what we want and how we make it. Let's consider again this set T. Consider this set. And let us, for each term of this set, consider a random event, namely independent twin cosines. So Z A independent variables coin tossing. So Zk take values 1 and -1 with probability 1/2. Yeah. So K and -1. So our probability space omega, all possible outcomes of all this coin tossing. We have 2 outcomes for each and n points. So equals -1, 1 to the power n. This is our omega. Now let us take P and Q and such that just and define the following sum: S P U omega equals 1 over square root of n from P to Q minus 1. So consider this sum, and this is a good normalization. So we have these sets S. Yes, and now consider the S is a function of U. Now consider so S is itself a random variable. Yes, it is a function on omega. So S generates the sets of omega where the value of this S less than given U. So let us define A P U U equals omega such that S P U omega less than U. U in star R. And let us define W the smallest internal algebra containing all the sets A, P, Q, omega. So, okay. Now, if you have this internal algebra, then we can, and on this internal algebra, we have a counting measure. Mu W. What does mean counting measure? W is the algebra of sets in omega. Yes? Mu of B equals number of B of omega. No, number of elements of omega is 2 to the power n. Yes? Number of elements of B is whatever it is. So we have this. And we have everything ready to use the Loeb measure. So we have omega L of W mu L corresponding again, here it all depends, all hinges on internal sets. Yeah? So we cannot do nothing if you have not internal sets. Then you have simply very large and untractable sets. And here we use this internal structure. Instead of mu L, let's write P. P is new probability. It is a standard. This is a non-standard number. This is already a standard probability. And now we have to work with different probabilities. Different probabilities and see what will happen. We have all definitions at hand, so let us see what will happen. So let us define, we have to still have to define the white noise. Now to be sure, let us suppose that this number n looks like k factorial, or some yes. So why I need it? Because in this case we have the following usual Q is contained in T. Because if a number is k factorial, this means that n is divisible by any standard integer. Yeah, no, and some non-standard, but any standard integer. This means that it contains all the rational number with a standard finite denominator. Yeah, and it is very convenient for us. Yes, and now if A and B are rational, yeah, we define the following thing. Side AB, no, of omega equals standard part of S of n times A, n times B, omega. So n times A is exactly P, and this is Q, so that P divided by N and Q divided by N are correspondingly A and B. So therefore I need to have exactly these endpoints, because we from the beginning have this internal set, internal function. And now we take standard part. So everything is well defined. And now let us check what will happen with this. So each S is a sum of plus minus ones, yes, random and independent, divided by normalizing factor square root of n. If you take two non-overlapping segments, yes, if you take A less than B less than C less than D, then certainly C A B is independent of C D. No, simply because they are sums of independent variables Z. Yes, so are independent. Now, what about, yes, and the second. Second is, if you say A less than B less than C, then C A B plus C of omega B C of omega. So we first take the sum of Z from A to B, or A times M, NA to NB, and then added the sum from B to C. No, certainly the result is the sum from A to C. Yeah? So this goes tautologically, equals C A C omega. Now the third, it is Gaussian distribution. No, I think here we have to follow straight forward way, namely we consider first the finite number of points in C. Yes? If T equals 0, 1, 1 over n, n minus 1 over n, and n is a standard number, yes? And then we can find probability, we can find this sum, exactly. We can find what is the probability that this sum is exactly given number. It is given by binomial distribution. Yeah, so probability of S P U what else? Omega. One moment, is less than U is equal to sum so we have to find the probability. Let me write better this. Equal m divided by square root of n. Yes? Let us take this. Equal 2 minus n nm. Simply sum. Is it correct? Just a minute. If it is 0, so it should no. In n n minus n over 2. N over 2 minus n. So it is maximum when m equals n over 2. Now we have this formula. Then we use the Stirling formula, yes, to estimate how does it look approximately when n and yes. So we use the Stirling formula, and we have what is called local limit theorem, just for one value equals exactly this. Then you can. It looks already asymptotically like the Gaussian function. Then we consider probability that this is less than some less than some n, less than some u, is the sum of corresponding values of this. Yes, then you replace this sum by integral and get approximate formula with some remaining term. Yeah, it is what is done in the course of probability. And then you will have the formula, and then you can apply this formula for non-standard n. And we will get the result. It is the simplest case where the central limit theorem works for the sum of independent plus or minus ones. That's it. What else? No, that's it. So this way we constructed the system of these random values, and in fact it is done for A and B rational, and we need to prove that this function, in fact we have this function CAB of omega, it depends on A and B. So how to prove that it is for almost all omega, it is continuous in A and B. There's also, so this function is given on, defined on the rational A and B. No, this is a theorem. So let me give a definition again. W of T omega equals psi 0 T of omega. Yes? And we have to prove that for almost all omega, W of T omega is a continuous function. That it is a continuous function. proof is we already know that for rational t, this is a Gaussian variable, Gaussian random variable. Yes? So we have to, okay, how it is done? Let us take t and equals 1. Okay. So we have this partition. Just take a partition. So t I are rational. Yeah. And we want to estimate the following quantity. T k plus 1 C T k T k plus 1 of omega. Cube. Just take 1k. And now this quantity, this C, is distributed by Gaussian law. Yeah? So distribution looks like this. And so if you consider probability of the following thing more than u, yeah, then this probability is given by the formula t minus s tk plus 1, no, delta tk to the power 1/2 integral from u to infinity e minus y squared divided by 2 delta tk dy. Yeah. One moment. Integral from u to the power 1/3, of course. Now how we can estimate? It is less or equal 1 or 2 pi delta tk power 1/2 e minus u to the power 2/3 divided by 2 delta tk. Now let's look. exponent decreases very fast. Yeah. So if you take u equals delta tk to the power alpha, yes, then you have equals 1 to pi delta tk to the power 1/2 e minus delta tk 2/3 times alpha divided by 2 delta tk. So if 2/3 alpha one moment. One moment. Beta 2 over beta 2 over beta times alpha 2 alpha. So if 2 alpha divided by beta more than 1, then you have equals 1 over 2 pi delta tk 1/2 e minus delta tk 2 alpha divided by beta minus 1 minus this minus delta tk to the power gamma. Gamma equals 2 alpha divided by beta minus 1. Yes, and certainly that gamma more than 1. And now you see that this function decreases so fast when delta tk goes to, just a minute, no, it should be less than 1. So this means that gamma less than 0, or gamma less than 0. So this means that if I take alpha equals 1 half, beta is 1/2, beta is 2, so if alpha less than 1, okay, no, we can make it negative. Yeah, so let us take beta equals 2, alpha less than 1. Then all this becomes, when delta tk goes to 0, this probability goes to 0 very fast. So this means that this probability is very small. So probability that the value of the function jumps very high is small and goes to 0 like this, because this factor is negligible here. And now, yes, this means that probability of the following Tk plus 1 to the power beta more than u for all k, yeah? So here we estimate probability on 1 second. If you do it on all, for all k, if you have the probability of this on 1 segment is very small, then probability on this here is also very small, and so on. So probability that it happens anywhere is more or less the sum of these probabilities. These are independent events. Yeah. Also very small. So this means that it goes to 0 as n, the number of these points, or partition points, goes to infinity, goes to 0 very, very fast. Yes? So we have this, and now the last thing is the following. Consider this W of T omega, yes, and consider this sum, say sigma, not sigma, S like this, n equals sum module module W of T k omega minus W of T k plus 1 omega to the power beta k from 0 to n minus 1. Yeah, so consider this sum Sn. So it says something about the sort of approximate continuity at the points of partition. So at this point, these differences cannot be very high. Yeah, because we know that probability that this is more than something, or here, and so at least one of these events are very small, and goes to 0 fast as n goes to infinity. As n goes to 0, as n goes to infinity, faster than n to the power minus alpha or any alpha. Yes? So as n goes to 0 very fast. And now consider the following event that as n more than, say, u, for some fixed u. And here we have one great theorem in probability. Which is called Borel-Cantelli lemma. Suppose that you have a sequence of events, say A1, A2, and so on, sequence of events. And suppose that the series sum probability of AK converges. So these probabilities go to 0 fast enough. Then for with probability 1, only finite number of events AI happens. Yeah. So it is one of the greatest theorem in probability. And so in our case, these Sn events Sn happen with probabilities which go to 0 fast enough so that the series converges. And then for almost all omega, or almost all omega, in omega, only finite number of these events happens. There exists n of omega finite such that Sn less than or equal than u for all n more than n of ohmic. So what does it mean? It means that if you take this n0, it gives us some partition. Yes? And on this partition, and in all smaller partitions, we can consider partition as divide all elements into equal halves. Yes, then again into and so on. For all these partitions, this sum not sum, maximum model x k plus 1 minus xk to the power beta less than u for k less than n for n of n more than n of ohmic. Yeah. This means exactly that this means that at the distances 1 over n0, unless the value of this, the oscillation of the function w is less than u to the power 1 over b. Yes? And now this way we can reduce u and have that for almost all omega. It happens for smaller some smaller distance. We have this. So we have we cannot say that this event that on some interval we have the high this high sum, so this means that our linear process has high jump. It can happen, yes, but probability of this is small. It can have a positive probability of this jump, but nonetheless, inside this jump, it is remains continuous. Yeah? No, it is a little more involved theorem that the Brownian trajectories or realizations of linear process are continuous with probability 1. So it is a delicate theorem, yes, but it is first proved for these finite systems, and then is transferred by transfer principle to our true linear process which we construct using our machinery. Okay, so this is no, I cannot because I don't know go far into the theory of linear process and random process. So my goal was to construct it, to show how it is constructed and how the non-standard methods work here. So next time I wanted to show more exotic random processes which are not so well known. So see you next time.